All right. So we're going to have two cuts. We have this 40,000, negative 5,000. We have an upward force of 14,905. Over here we have negative 40,000, negative 5,000. Oh. Just 2452.5 newtons per meter. Okay. And so now we're going to do the two cuts. Cut one, I'm not going to go through all the steps because I want to get this stuff all down. But so we have, this is what we're doing the calculation from. Negative 40,000, negative 5,000. A downward force, point force of 2452.5x. T, V, and M. And I got a value for T of negative 40,000, V of negative 2452.5x minus 5,000, and M of negative 1226.25 x squared minus 5,000x. Okay, so that's for cut one. The derivatives work out with that, so that makes sense. The moment is 0 at the when x is equal to 0, so that makes sense. Then cut two. You have 40,000, negative 5,000. A point force of 2452.5x. Another point force here of 14,905. And then the internal loads. Question? So T is negative 40,000. So as far as the tension compression, what's that, a tension or a compression? Compression, which means that if we're looking for the point with, so remember we're going to end up adding the normal stresses due to tension compression and due to bending. And so so if you're the place where the normal stress due to tension and the normal stress due to bending are going to be in the same place is when you have a compressive stress due to the bending, okay? Because you have compression here due to the axial force. Shear force is negative 2452.5x. Nope, that's the wrong one. 2450. Okay, x plus 9,905. And then the bending moment is equal to negative 1226.25 x squared plus 9,905x plus 14,905. And again, the derivatives work there. You end up, when x is equal to 2, this is 0, so that makes sense. that should be, so it's positive in Newton's second law, but then when you move it to the other side of the equation, yeah, that should be negative, right? Okay, so did any of you guys graph the bending moment diagram? So it looks something like this. So if this is negative 6,226, it looks like that. Okay, so we're going to expect the contribution to tension or compression to be biggest right at that point force. That causes one issue with interpreting this. What's that? So this is something that you always have to keep in mind when you get this. Remember, St. Venant's principle says the closer we get to a load, the less we trust it. This is saying the most critical part of this beam is right at that load. And so we're going to do this calculation, but you have to recognize that we're not going to get exact values here. Okay? You understand why I say that? Okay. So the next thing we have to do, it's time to go. But the next thing we have to do is calculate, let's just finish it next time.